Okay, so we are good to go. So this is about the homework. Homework number 8. So last two problems. So the idea is the following. So let's say you have a function f. So I'm gonna do a similar problem. So let's say f of x is equal to cosine, or let's say x to the power x. Okay, x to the power x. So the thing is, when you have x to the power x, this is not. So this is not an exponential function, right? This is not an exponential function, because when you have an exponential function, you would have some constant to the power x. All right. So for exponential functions, you would have like a to the power x, right? Some constant fixed number to the power x. The thing is here in the base, I mean, you have x, of course, an exponent, but in the base here, this is not a constant. That's your variable x, right? This is not a constant, right? It's your variable x. So in this case, so this function f of x is not an exponential, right? So this is not exponential function. All right, so so the idea is the following. So whenever you have x in the, so when x is in both the exponent and base, okay, so x is in the exponent and x and in the base, right? And the base. Okay, so we have to apply. We apply the log trick. So we apply the log trick. Okay. So this is again, this is like in the last two problems in the homework. So if you check the last two problems in the homework, the variable x is in the power, right? And also in the base. So in the base, either, so we have x to the power 1 over x. So we have, so x is in the base, or we have sine of x to the power x. So in the sine of x, there's x, right? So you have an x in the base, right? So in both cases, you have to apply the log trick. So what's the log trick? Well, the idea is the following. So you have your f of x equal to x to the power x. And so what we do is we apply natural log to both sides. So here's a natural log and here a natural log. And the thing is, because when you apply a natural log, you can bring down the power. So this this x here in the power, you can bring it down here in front of the natural log. So we're gonna have natural log of f of x equal to x times natural log of x. Okay. Now, once you bring down the power, now you compute the derivative. Okay, so now you compute the derivative. So take the derivative. Okay, derivative, both sides. So on the left side, what would be the derivative of natural log of f of x? Okay, so I have to remind you the following rule. So whenever you have natural log of some function, let's say some function g. Okay, so let's say you have so h of x h of x equal to natural log of some function g of x, all right, then the derivative h prime would be, and this is the consequence of the chain rule, okay? So then h prime would be g prime of x over g of x, okay? So this is, so this f here, this is like my g here, right? I have a natural log of f or natural log of g, and what I'm saying is that the derivative would be g prime over g, right? So in my case, I have natural log of f, so the derivative would be f prime over f, right? So then on the left side, we're gonna have f prime of x over f of x, okay? That's because I applied this rule here, right? So this is saying the derivative of natural log of f would be f prime over f, okay? Now the right side, it's x times natural log of x, so it's a product. So we have to apply a product rule. So this is here, we need to apply a product rule on the right side. So that's the derivative of x times natural log of x. Derivative of x is 1 times natural log of x plus, and then x times the derivative of natural log of x, right? Again, product rule, this is f, this is g, f times g. So then you will have f prime g plus f g prime. So what will be the g prime? Well, g is natural log of x. So then g prime, derivative of natural log of x, is 1 over x. Okay, so that's my product rule. Now,
I'm sorry, Professor, how did you get 1 over x again?
That's because
Where'd you
that's
get 1 from?
The 1 over x, the 1 over x, that's the derivative of natural log of x. So you see my g, this is my g, right? And this is my f. And yeah. I'm applying the product rule. So that would be f prime times g plus f times g prime. My f is x and my g is natural log of x, right? And
so then for the 1 times ln x, you just did the x is a 1, right?
Yes.
So
yes.
1 times, okay.
Yes.
And for the second one,
because
for the second one, x is that x. What's the 1x?
Yeah, but because so your f is x, right? So first here, the 1, that's because that's the derivative of x. Derivative of x is 1, okay? Times g, that's g is natural log of x. That's ln of x, natural log of x. Then you have, this is product rule, right? So then you have f, which is again x, and then g prime, but g is natural log of x. And we know that derivative of natural log of x, natural log of x, we saw that derivative of natural log of x is actually 1 over x.
Oh, so in the log over x, that belongs to the 1 over x.
Yes. That's the 1 over x, that's the derivative of natural log of x. Okay. So this is like, we had a couple of rules how to compute the derivative, like for natural log of x and also for exponential of x, right? So for natural log of x, the derivative would be 1 over x. All right?
Okay, thank you.
Sure. And then, okay, so then you have f prime over f. 1 times natural log of x is just natural log of x, right? 1 times any, anything is going to be it's just the same thing. So it's going to be natural log of x plus, and then x times 1 over x. Well, then x over x, it cancel out, right? This, this x here in the top, this one here, and the one in the bottom, they cancel out. So that will be just 1. Okay. And again, the goal here is to compute the derivative of f, right? We want to compute f prime of x, right? So I need to solve for f prime of x, right? That's because that's the exercise. We want to find f prime of x, so we have to solve for f prime of x. That's our goal, right? Find derivative of f. So then for f prime of x, all you have to do now, of course, is just to multiply both sides by f. So here by f and here by f. Of course, the whole thing here by f, right? Both sides by f. So if you multiply left side by f, of course, your f here just cancel out. So that will be just f prime. And then on the right side, so we're going to have equal f of x times natural log of x plus 1. Okay. Now, last thing to do now is just to substitute this f of x because, well, we know what's f of x, right? F of x is supposed to be, this is my f of x. My f of x, that's my original function. That's x to the power x, right? That's my original function, right? So here I can just substitute. So with you know, f of x, we know that's my initial function. It's x to the power x, right? So then the derivative f prime of x would be x to the power x times natural log of x plus 1. And that's the final answer. All right. So guys, in the homework, you need to apply the same, you know, the same trick, a natural log for the last two problems. Apply natural log to both sides, and then, you know, it's gonna be almost the same steps, right? This is just the same steps. Just be careful with the product rule. When you apply the product rule on the right side, left side is gonna be the same thing. It's gonna be f prime over f, right? And then you solve for your f prime. Does this make sense to you, Tasha? I mean, any question?
It does.
All
I
right.
have one question. So when you stop at the derivative of that's not the full answer, right?
Where? You mean here? I'm sorry. You mean here?
Yeah.
No, the thing is, because I know, yeah, that's not the answer. This one here, the answer, because I know what's the value or what's the expression of f of x. F of x, that was my original function, right?
Right. Okay.
That's my original function. I just substitute my f of x with my, you know, my original function, x to the power x.
Okay.
Mm-hmm.
This makes more sense now because I
Okay,
saw
perfect.
this in another where you did it again, but I didn't quite get it.
Okay, actually, I think I did probably. I mean, if you check the recording, I think, or the notes, I think I did probably 2 or 3 similar problems.
Yeah, you did.
With the cosine of x. Mm-hmm.
Yeah, but I didn't get it. But now it's much more clear to me.
Mm-hmm. Sure. All right. Is there any other question, guys, about the homework? All right. So I'm sorry. Is there any question?
No.
Oh, okay. Sorry. Probably I have to probably mute. Okay. All right. So then let's move to the to our chapter 3, right? So this is section. We are still in section 3.1, and it's about the mean, max, minimum, and maximum values, right? So I think on Monday I introduced the, you know, the definition of absolute or global maximum and absolute and global minimum, right? So just to remind you, so on Monday, so I introduced the notion of absolute or global maximum, and also the same thing for minimum, right? Absolute or global minimum. So we said an absolute maximum would be like the highest point of the graph, right? And an absolute or global minimum, that will be the lowest point in the graph, right? So that's basically the idea, right? Now, Next, we're gonna have now what we call a local maximum or relative maximum, and also local minimum. Okay, so well, first let me just introduce a local maximum. So here's the definition. Okay, so function f function f of x has a local maximum at a if f of a is larger or equal than f of x, okay, for any x close, or for any x in the neighborhood of a, for any x close to a. Okay, so here you have to be careful, guys. So here I'm using the word local maximum because I'm interested in the values of x which are close to a, right? So for example, let's say I have the following graph. Okay, so let's say I'm gonna start from the bottom here. All right, so let's say this is my f of x. The arrows, guys, the arrows means that they mean that the graph actually continues, right? It doesn't stop. It goes all the way down. Okay. So let's say this is my f of x. All right. Now, do we have a global maximum? Any guess? Do you think, guys, we have a global maximum? So remember, guys, global maximum, that will be the highest point of the graph, right? So here in this graph, of course, this point, you see this point here, this would be a global, so this point here would be a global maximum, right? Okay, because that's the highest point of the graph, right? Now, do we have a local maximum? Well, yes, because, so you see, guys, here at this point here, this one here, you see at this point, so what happens here is that if you take a small neighborhood of your point, of your A, so if you take this neighborhood here of your point, all right, then the corresponding values of the function f, so you see here, the corresponding values, so you see the corresponding values, they're gonna be lower than your green point, right? So this one, this point here, this one here, that will be a local maximum, because again, because you know, if you take a neighborhood, a small neighborhood of your point, then the green point would be like the highest point, right? If you take just a small neighborhood of the point, right? So that's why it's called local, because it's just you know, for some small neighborhood around the point, right? It's not a global maximum, right? It's not the highest point of the whole graph, right? It's actually the highest point in this small neighborhood, right? In this, you know, in this small neighborhood of the point, right? So so the idea is whenever you have sort of, so the idea is whenever you have like a
Professor,
parabola, yes?
so sorry to interrupt you.
Yeah,
The
sure,
one
please.
over x, the derivative of one over x is x negative one.
Derivative of 1 over x. Well, 1 over x, it's like x to the negative 1. So you can apply the power rule. So then the derivative would be minus x to the negative 2.
Okay, so
Or minus 1 over x squared. Yeah, Austin. Austin is correct. That's the answer. So yeah. So
okay,
it's
thank you.
negative 1 over x squared. Yes. Sure. Yeah. So the idea, guys, here is that so when you have a like a sort of a parabola, whenever you have like a parabola, which opens downward, like this one here. Okay, so whenever you have such a parabola, then this point would be a local. This point here would be a local maximum. Okay, so whenever you have a parabola which which opens downward, okay, then you would have a local maximum. It doesn't matter what happens to the rest of the graph. So for example, you could have like a higher points than your local maximum, right? But it doesn't matter because you are interested in just a small neighborhood of your point, right? So if you take this small neighborhood of your point around your point, then your point would be like the highest one, right? In this small yellow, neighborhood of your point. Okay. So again, the idea is whenever you have like a parabola which opens like downward, so then the vertex, that will be a local maximum, right? Now, yeah, so now we have the same for a local minimum, right? So so I can probably introduce a local definition of a local minimum. Well, first, is there any question, guys, about this local maximum? So you see the difference between local maximum and the global maximum, right? All right, so then, so now I can introduce local minimum. So it's the same idea. So a function f of x has a local or relative, has a local minimum at a if f of a is less or equal than f of x for x in the neighborhood of a, or for x close to a. Okay. So the idea is, oh, sorry. So the idea is, of course, is the following. So whenever you have like let's say you have this graph here, and somewhere you have like a parabola which opens up. Okay, so like let's say you have this parabola here. All right, so then this vertex, this point here, this one here, that will be a local minimum, right? Because if you take a neighborhood of the point, if you take this like a small neighborhood around the point, then your point, the blue one, would be the would be the lowest point in the small neighborhood, right? Of course, you don't really care what happens to the graph like far away from your point. So for example, let's say you have something like this here, right? Then of course, this point, this one here, this would be a global minimum, right? This one here would be a global minimum because that would be like the lowest point on the whole graph, right? But for a local minimum, you don't really care about the what happens to the graph far away from your point, right? So you're just interested in a small neighborhood around your point. So around my point, if you take a small neighborhood around your point, then your point, so here, this is your point here. And so in the small neighborhood of your point, the blue one would be, the blue point would be the lowest point in the neighborhood, right? So anyway, yeah, so the idea again is just whenever you have like a parabola which opens up, okay, then the vertex would be like the local minimum, right? Any question, guys? So you see the difference between the global minimum and local minimum, right? Now, okay, so now the goal is to find, we want to find local maximum and minimum of a function f. So now, so next, so what we want to do is, so now the goal is to find, so how can we find the local maximum or local minimum of f of x, right? So, well, so then we have actually the following theorem. So we're going to use the theorem to find the local maximum and the local minimum. So we have the following theorem. So the theorem says the following. So suppose that we have a function f. Okay, so suppose that f is differentiable at a. Okay. So when I say f differentiable at a means f prime of a exists, right? F prime of a exists. Okay. So then if f has a local maximum or minimum at a, then f prime of a is 0. Okay, so if f has a local maximum or a local minimum at a, then f prime of a, the derivative at a must be 0. At a, okay, then at a, then f prime of a must be 0. Okay, so what we are saying, guys, is that if a function has a local maximum or local minimum at some value a, then the derivative of the function must vanish at a, okay? The thing here is just be careful. The fact that the derivative is 0 at a, it doesn't mean that f has a local maximum or minimum at a. So just be careful. So this is a warning. Okay, so f prime of a equal to 0. It doesn't mean that f of x has a local maximum or local minimum at a. Okay, So if you have a local maximum or local minimum at A, then derivative is zero. But if the fact that derivative is zero, it doesn't imply that you have a local maximum or local minimum, right? So here's an example. Okay, so first example, let's say f of x is equal to x cubed. All right. So just to remind you, the graph of x cubed. So the graph of x cubed is, it looks like the following. So this would be like the graph of x cubed, okay? This is f of x equal to x cubed, right? Now, what's the derivative of x cubed? Well, f prime of x, derivative of x cubed, it's just you bring down the power and you subtract 1 from the power. So that'll be 3 times x. You subtract 1 from the power, so that'll be 3x squared, right? So this is f prime of x. Right? But then, so you see, guys, what will be f prime of 0? F prime of 0 is, of course, 3 times 0 squared, which is 0. So I'm saying that f prime of 0 is 0. But you can see here, at x equal to 0, so here's my 0, right? This point here, it's neither a local maximum nor a local minimum, right? So this is, it's neither maximum, local maximum, nor local minimum, right? So the fact that the derivative is equal to 0 at A, it doesn't mean that that f of x has a local maximum or local minimum at A, right? So here, what I'm saying is that, so the fact that f prime of 0 is equal to 0, it doesn't imply that f of x has a local minimum or local minimum at 0, right? So it doesn't apply that f of x has a local maximum or local minimum at 0. Okay, and you can see it from the graph of x cubed, right? 0 is not, it's neither local maximum nor local minimum, right? Well, let's take another example. Example number 2. So let's say f of x is equal to x squared, right? So x squared, of course, the graph of x squared would be a parabola, right? So the graph of x squared would be a parabola. So it would be this parabola here, right? This is x squared. Now, do you see a global maximum or global minimum here, guys? Is there a local or global maximum or a global minimum? Yes, there's a global minimum, Adrian, absolutely, at 0, right? So this point here, there's this 0. So this point here is actually global, a global minimum, right, at 0. Okay, and so our theorem says that because we have a minimum at 0, then the derivative of f is going to be equal to 0 at 0. Okay, so our theorem, so the theorem implies that f prime of 0 is going to be 0. Okay, and that's of course true. So we can, and that's true, right? This is true, right? Because if you compute f prime of x, because f prime of x would be derivative of x squared would be 2x, and so f prime of 0, that would be 2 times 0, and that would be 0. Okay. So you see, so the theorem says if you know that you have a minimum or maximum at a, then the derivative is going to be a 0 at a. Okay. But the converse is not true. So if you know that your derivative is equal to 0, vanish at a, it doesn't mean that you have a maximum or minimum at a, right? Okay. So anyway, the numbers, you know, the numbers where the derivative is 0, okay, they are kind of special numbers, and they're called critical points. Okay, so so the numbers where, so this is definition. So I'm gonna suppose first that f prime of a exists. So suppose f prime of a exists. Okay. Then a is called a critical number, or a critical point. Then a is called a critical point if f prime of a is 0. Okay. So so what I mean by critical points is the values of x where the derivative is 0. Okay. So of course, so if you have a critical point at a, it doesn't mean that your a is a global, is a minimum or a maximum, right? But if you have, of course, if you have a minimum or maximum, then your a, of course, is going to be a critical point. Okay. Anyway, so so what we're going to do next, we're going to try to find, as I said, our goal is try to find minimum and maximum of function f. And so so what you have to keep in mind for the moment, guys, is that if you have a local maximum or local minimum, then the derivative, then a would be a critical point. Then the derivative is going to be equal to 0, right? So just keep in mind that if a, or if f of x okay, so if f of x has a local maximum or local minimum at a, okay, then a is a critical point. Okay. And again, what do I mean by critical point? I mean f prime of a is 0, right? That's just the definition of critical point. It means that f prime of a is 0. Okay. Anyway, now we're going to try to find global maximum and minimum in when we have let's say closed interval. Okay, so so what we're going to do now, we're going to try to find global maximum global minimum on in a closed interval. Okay. So to find this global maximum, global minimum in the closed interval, so we're gonna use the following theorem. So what does it say? The theorem, it says that if f is a continuous function on a closed interval. So if f of x is continuous on a closed interval AB, closed interval AB, then f of x, then f of x actually attains an absolute or a global maximum and a global minimum in the interval AB. So a global maximum and a global minimum in the interval AB. Okay. So what does it say in the theorem? It says that whenever you have a function, so the idea is the following. So whenever you have a function which is continuous on some closed interval AB, so you have like, so you have A somewhere here, and you have your B somewhere here, okay? And then let's say this is f of A, this is, let's say, f of B, all right? So then this is f of A, and this is, of course, this is f of B, right? Then, you wanna connect this 2 points, A and B, all right? Let's say we're gonna have something like this here, okay? So this is a continuous function on the interval, on the closed interval AB, right? This is this is your interval AB here, okay? So this is your f of x. So then you know that this function f, because it's continuous. This is a really important assumption, that the hypothesis that it's continuous is very crucial here. Then because it's continuous on this closed interval AB, then you know that they exist. Then f has a global maximum. For example, this point here, that will be your global maximum. This is your global maximum. And this one here would be your global minimum, right? So again, the important hypothesis here is that you have a continuous function and on closed interval. This is important too, okay? So you need a closed interval. So then you're gonna have a global maximum and a global minimum, both, okay? Now guys, so now I'm gonna show you the examples, with the explicit examples, how to find this global maximum and global minimum on a closed interval AB, okay? So let's say we have the following example. Okay, example. So let's say f of x is equal to, so I'm going to take a polynomial. So let's say it's x fourth minus 2x squared plus 3, all right? in the interval, let's say -2, 3. Okay, so I have this function f, which is a polynomial, and so because it's a polynomial, so it's going to be continuous on the interval -2, 3, right? So you can just, I mean, you can imagine you have the graph of f of x would be something like, I don't know, let's say this is -2, this is +3, and what I'm saying is that here's your f of x, okay? Let's say this is f of x, your f of x. Now the goal is we want to find the global maximum and the global minimum, okay? So we want to find the global maximum and the global minimum, okay? So I'm going to show you the steps, how to find the global minimum and the global maximum, right? So step 1, so this is your function f, and you want to find the global maximum and global minimum, right? You want to find these 2 points here. This one, you want to find this would be probably your, your global minimum, and this one here, that will be your global maximum, right? This is your maximum here, and this is your minimum, right? And you want to find these the global maximum and global minimum. So step 1. So we're gonna do first. Step 1, you have to find the critical points of f of x. Okay. So again, what does it mean, critical point? So that's where the derivative is 0, right? So where f prime of x is 0. So we have to solve. So we have to solve f prime of x equal to 0 to find the critical points. Okay, so we have to solve f prime of x equal to 0 to find the critical points. But remember, guys, if you have a critical point, I mean, if the derivative is 0 at a, it doesn't mean that your that your function f is gonna have a maximum or minimum at a, right? That's not enough, right? Finding the critical points, it's not enough to find the global maximum and global minimum, because remind you the example with x cubed, with the example of x cubed, it's the derivative is going to be 0 at 0, but 0 is not, it's neither a maximum nor a minimum, right? So finding the values of x where the derivative is 0, it's not enough to find the global maximum and global minimum. However, you know that if you have a global maximum or global minimum at a, the derivative is going to be 0, okay? So yeah, just be careful. Anyway, so that's the first step. So we're going to find the critical point. So we have to solve derivative is 0. So then what's the f prime of x? So f prime of x, well, it's x fourth, so that will be 4x cubed minus 2. So we keep the constant 2, right? 2 times x squared, the derivative, we keep the 2. And then we derive the x squared. Derivative of x squared is 2x, so times 2x plus 3. Derivative of constant by itself is 0, right? So, so you know your f prime of x is going to be 4x cubed minus 4x. Okay, and so again, we have to solve f prime of x equal to 0. So how do we solve this f prime of x equal to 0? Well, we can, well, it's, so the highest power of x here is 3. So it's not a quadratic equation. We cannot use a quadratic formula. So we have to factor, right? And the common factor would be, you know, x. X is a common factor. Actually, better than x, it's 4x, right? So I can factor out 4x. So 4x times, and then x squared. 4x times x squared, that's 4x cubed minus 1, right? Equal to 0. So remember, guys, what I'm doing here, I'm trying to solve f prime of x equal to 0. That's the first step, as I said, if you want to find your global maximum, global minimum, right? And so you have a product equal to 0, then either one of the factors is 0. So either 4x is 0, or you know, the x squared minus 1 is 0. Okay. So 4x is 0, then your x is equal to 0. X squared minus 1 is 0, then x squared is equal to positive 1. Then you have to get rid of the square. You apply square root. So here's my square root, both sides. But because it's an even power, then you need the plus or minus, right? So you have x equal to square root of 1 is 1. So it's plus or minus 1, right? So x is 1 plus 1, or x is negative 1, right? So I got 3 solutions, x equal to 0, x equal to positive 1, and x equal to negative 1. All right. Now, so that's the first step. So the answer here, the critical points, or the critical points of f of x are, so we have x equal to 0, x equal to positive 1, and x equal to negative 1. Okay. Now, step number 2. So I got my critical points. Now, step number 2, I'm gonna try to find. So step number 2, I'm gonna try to find the values. Find the values of f of x. Values of f of x at the endpoints of the interval. And the critical points, and the critical points inside the interval, in the interval. Right? So, so my f of x, it's the, you know, it's the x fourth minus the 2x squared plus 3, right? And the interval is -2, 3, right? So I have to find, first, I have to find the values of f of x at the endpoints of the interval. So endpoints of the interval, so it's -2 and positive 3, right? That's the endpoints of the interval. So I have to evaluate f of -2 and f of positive 3. Okay. So f of -2 would be, you know, -2 fourth minus 2 times -2 squared plus 3. So that would be -2 fourth, that's 16. 16 minus 8, that would be positive 8 plus 3, that would be 11. Now, what about f of 3? So that's 3 fourth minus 2 times 3 squared plus 3. So 3/4, that will be 81. 81 minus, so 3 squared, that will be 9. 9 times 2, that's 18. All right. So 81 minus 18, that's 63, plus 3, that's 66, right? Now, next, I have to find the values of f of x at the critical points which are inside the interval. So remember my critical points, guys. I got a 0, I got +1, and I got -1, right? So I have to evaluate my function f at 0, +1, -1. But just be careful. Your critical points, they have to be inside the interval. 0 is inside the -2, 3, so that's okay. +1 is inside the interval, and also -1 is inside the interval. So your critical point must be inside the interval. If it's not inside, then don't evaluate your f at the critical point if it's not inside the interval, okay? So all of them, all my critical points are inside the interval, -2, 3. Okay, so my critical points, x equal to 0, x equal positive and -1, all of them are inside my interval, are inside, or they belong to my interval, right? So they belong to the -2, 3. So I'm going to evaluate f at 0, f at 0, then f at +1, and then f of -1. So f of 0, that's 0/4 minus 2 times 0 squared plus 3, that's +3. F of +1, that's 1/4 minus 2 times 1 squared plus 3. That will be 1 minus 2, that's -1 plus 3, that's +2. And f of -1, -1/4, that's positive, so -1/4 minus 2 times -1 squared plus 3, so that's +1 minus +1 minus 2, that will be -1 plus 3, that's +2, right? Okay, so I evaluate my function f at the endpoints of my interval and at the critical points inside my interval, right? So now the step 3, I can find my absolute maximum and absolute minimum. So the absolute maximum would be the largest. So then my absolute maximum corresponds to the largest value of f. And the absolute minimum or global or absolute, the absolute or global minimum, that's the smallest value of f of x. So I have to compare all the values I got in the step 2. So I have 11, I have 66, I have 3, I have 2, I have 2. So which one is the largest one? That's the 66, right? So you see, guys, this is 66. That's the largest value. That's f of 3. So 3 would be, so my f of x, so f of 3 is 66, is the largest value. So f has a global or absolute maximum at x equal to 3. Okay, now what will be the smallest value? If you compare the values I got in the step 2, Well, the smallest values actually we have, well, two of them, right? Here, two when my x is equal to 1, and also I get 2 when my x is equal to -1. So I got actually two absolute minimum. So f of 1 is equal to +2. F of -1 is also +2. So this is the smallest value. So f of x has a global or absolute minimum at x. Well, actually, we have two global because they have the same height, right? Both are of height 2, right? So we got actually two global minimum at x equal to +1 and x equal to -1. All right. So that's how we find global maximum and global minimum of a function f on a closed interval. Any question, guys? So you see the three steps. Step 1, you'll find the critical point, the critical points. And again, if you have a critical point, it doesn't mean that the point would be maximum or minimum. Step 2, you have to find the values of the function at the endpoints and also at the critical points. And then you have to compare all these values, right? You compare them, and so you get your global maximum and global minimum. So here you see, guys, for example, 0 is supposed to be a critical point, a critical number. F prime of 0 is 0. However, f of 0 is d. That's it's neither a global maximum nor a global minimum, right? So again, it's not because your function or derivative of your function vanish at the critical point. It doesn't mean that the critical point would be a global maximum or global minimum. Anyway, any question, guys? Okay, so then here's an exercise. So I'm gonna give you two functions, and you have to find exercise. You have to find their absolute maximum and absolute minimum. Okay, so find the absolute maximum and the absolute minimum of number 1, number 2. So first function f of x. So let's say f of x is 3x squared minus 12x plus 5 in the interval, let's say 0, 0, 3. All right, and second function f of x is equal to x over x squared plus 1 in the interval 0, 1. Okay, so please, guys, find the absolute maximum and the absolute minimum of these two functions. Okay, you can just follow the same steps I had in the example. All right. So you have, let's say, 10 minutes, 10, 15 minutes to think about this exercise. All right. And I'm gonna be here to answer your questions if you have any. So let me know, guys, if you have any question. So first step, you have to solve f prime of x equal to 0, right? You have to solve, as you can see here, you have to solve f prime of x equal to 0. So then you get your critical points. And then the step 2, you have to find the values of the function at the endpoints of the interval, and also at the critical points which are inside the interval. And then once you evaluate your f, I see there's a question, Austin. Yes, I think you're correct, Austin. Yes, very good. Yes, I think, let me see. Yes, 5 and -7. But just one thing. So when you answer the question, so when you get your global maximum and global minimum, then you have to specify the value of x, right? So here, for example, I got f of e equal to 66, which is the largest value, right? So I would say f has a global maximum at x equal to 3, right? Not 66. So when you write in your final answer, you should specify the value of x. Okay. But I think you're correct, Austin. I mean, I think the largest value would be 5 and the minimum would be -7. Yes. Yes. Yep. Absolutely. Yep. Yeah. 2. That's true. I think that's true. Yes. For number 2, guys, when you have a fraction and you want to solve the fraction equal to 0, you don't really care about the denominator. all you have to do is to solve the top, your numerator equal to 0, okay? So, you know, like number 2, your function f is it's actually a rational function, which means f is a quotient of polynomials. So f, you have a quotient. And so when you compute the derivative using, of course, the quotient rule, you know, then in the first step, you have to solve, you know, derivative equal to 0. So all you have to do is to solve the numerator equal to 0, okay? Because if the numerator is equal to 0, you have a fraction, and the numerator at the top is 0, then the whole thing is going to be 0. Oh yeah, by the way, guys, so don't forget your the extra credit. The extra credit, I think it's due December. I think it's December 2nd, right? If I'm not mistaken. Yes, it's December 2nd, right? Yeah, yeah. Just don't forget your extra credit, okay? All right, guys. Well, it's 7:30. Okay, so let's take a break of 5 minutes. All right, and then after the break, I will go over the exercise. Okay, so let's take a break of 5 minutes. All right. So I will be back at 7:35. All right. All right, guys. Yeah, so let me go over the exercise. So this is, let's move to the next page. So for number one, we had, so what was the function f? So f of x, it's a polynomial. It's just, 3x squared minus 12x, right, plus 5. In the interval, so we have the interval 0, 0, 3, right? Okay, again, so the goal is to find, we want to find our absolute or global maximum and global minimum, right? So we said first step, we have to solve, step one, we have to solve f prime of x equal to 0, right? So first you have to compute f prime of x. So what will be f prime of x? 3x squared, that's a constant times some function, constant times x squared. So we keep the constant, we keep the 3, right? Times, and then derivative of x squared. Derivative of x squared, bring down the power and you subtract 1 from the power. So there'll be 2x minus 12, keep the constant, times derivative of x is just 1. So it's minus 12 times 1 plus, and then there's a constant by itself. So then the derivative would be 0. Okay. So f prime of x, it's just 6x minus 12. And I want to solve, remember, I want to solve f prime of x equal to 0. So I want to solve 6x minus 12 is equal to 0. So then 6x is equal to 12. You divide by 6 over 6, both sides. So then x is equal to 2. Okay, so that's my critical point. So I got one critical point at x equal to 2, right? So f of x has a critical point at x equal to 2. Right? That's the first step. I got my critical points. The step number 2, I have to evaluate f of x at the endpoints. Step number 2. So evaluate f of x at the endpoints of the interval and at the critical points inside the interval. Critical points which are inside the interval. So, well, first, what's my f of x? F of x, we said it's 3x squared, minus 12x plus 5. So what's the interval? We have the interval, we said 0, 3, right? So my endpoints, the endpoints of the interval are 0 and 3, right? So I have to evaluate to check f of 0. So I have to check f of 0. So that will be 3 times 0 squared minus 12 times 0 plus 5. So that will be positive 5. Now f of 3, that's 3 times, 3 squared minus 12 times 3 plus 5. So 3 squared, that's 9. 9 times 3, that's 27. 12 times 3, that's 36. So 27 minus 36, that's negative 9. Negative 9 plus 5, that's negative 4. All right, that's f of 3. And now I got one critical point, which is x equal to 2. And 2, of course, is inside the interval that's inside the interval 0, 3. So because it's inside the interval, so I have to evaluate f of 2. So f of 2, that's my critical point. So what will be f of 2? So that's 3 times 2 squared minus 12 times 2 plus 5. So it's 4 times 3, that's 12. 12 minus 24, that's negative 12. Negative 12 plus 7, plus 5, that's negative 7. All right? So this is the value of my function at the critical point. All right? This is at the critical point. And here, that's at the endpoints. Right? This is at the endpoints. Anyway, so now in the last step, I'm gonna compare, see which one is the largest, so which one is the smallest value. So so then the largest value. Let's start with this largest value. So I got I got 5, I got negative 4, I got negative 7. So as Austin said, the largest value would be 5. So f of 0 is 5. That's the largest value. Is the largest value. Okay, so f of x has a global or absolute maximum at x equal. So in your answer, guys, in the test or in the final, you have to specify the value of x. So it's x equal to 0. All right, so it's at x equal to 0. All right, because my x here is equal to 0, right? Now, what will be the smallest value? I got negative 4, I got negative 7. So as Austin said, negative 7 would be the smallest. So f of 2, it's negative 7, and that will be the smallest value of f of x. So then f of x has a global minimum at x equal to positive 2. And that's my global minimum. So it's at x equal to 2. All right. Any question, guys? Nope. All right. Okay. So I can probably do the other number 2. But of course, here, guys, you need to know how to compute the derivative, right? That's really important because, in the first step, you have to compute f prime of x. So if you get the wrong derivative, then of course everything, most of the time everything else is going to be wrong, right? You will get probably the wrong answer, right? So you need to know how to compute the derivative because you have to solve this f prime of x equal to 0. So yeah, just be careful with the derivative because otherwise, we will probably end up with the wrong answer. All right, so okay, number 2, that's so my f of x is we said it's x over x squared plus 1. The interval is 0, 2. All right, so step 1, as usual, step 1, we have to solve f prime of x equal to 0 to find our critical points. Solve f prime of x equal to 0. So first, I have to compute f prime of x. All right. So how do I? Which rule I'm going to apply to compute f prime of x? Any guess? Quotient rule, Adrian. Thank you. Yes, absolutely. Thank you. Because your f of x is a quotient. right? It's actually a rational function. It's a quotient of polynomials. So we have to apply quotient rule. So this is a quotient. So we have to apply the quotient rule. Okay, so just remind the quotient rule. You have f over g. The derivative would be f prime g minus f g prime over g squared. Okay, so this is supposed to be like my f and in the rule, and this is supposed to be like my g. So let's compute the derivative then. So it's f prime, derivative of x, it's 1, times g times the x squared plus 1. There's the minus, so here's my minus, f, which is the top, it's x, times the g prime, the derivative of the denominator. So derivative of x squared, it's 2x, plus derivative of 1, it's constant by itself, so it's just 0. So it's just times 2x, right? Over x squared plus 1, g squared, so the square of this x squared plus 1, right? So anyway, so what I'm saying, guys, is that f prime of x, so it's going to be x squared times 1, it's x squared, plus 1 times 1, it's 1, minus x times 2x, that will be minus 2x squared, over x squared plus 1 squared. And so my f prime of x would be, so you see this x squared minus 2x squared, that would be minus x squared. And then there is plus 1. So here's my plus 1. All right, over the x squared plus 1 square. All right, so that's my f prime of x. All right, so I want to solve this f prime of x. I want to solve f prime of x equal to 0, right? So this is a fraction. I mean, this is a quotient. And if it's equal to 0, then whenever you have a quotient or fraction equal to 0, it means that the top is 0. Okay, so then the top is 0, right? Because if the top numerator is 0, 0 over any non-zero number is just 0, right? So if your top is 0, then the whole thing is gonna be 0. So I have to solve minus x squared plus 1 equal to 0. So then, so let's add, say here's plus x squared plus x squared. So what we are saying is that we're going to have 1 equal to x squared. Apply the square root. Here's my square root. Here's my square root. Because the power is even, then we need the plus or minus. All right, because the power is even. If it's odd, if you had x cubed, then you don't put the plus or minus, right? So whenever the power is even and you apply the nth root, then you need the plus or minus. All right, so then your x is just, so your x is just plus or minus 1. So it's positive 1 or x is negative 1. Right, so I got two critical points. So here for the first step, so f of x has 2 critical points. X equal positive 1 and x equal to negative 1. All right, so that's my critical points. Now, step number 2. So step number 2, we have to solve, we have to evaluate. So what's f of x? F of x is, it's x over x squared plus 1, and the interval is 0, 2, right? So here, just be careful, guys. So first, the endpoints. What are the endpoints here? The endpoints are 0 and 2, right? So I have to evaluate f of 0 and f of 2, because 0 and 2 are the endpoints. So this is at the endpoints. All right, so f of 0 would be 0 over 0 squared plus 1. 0 over 1, and that will be 0. 0 over a non-zero number is 0. Now, what about f of 2? That's 2 on the top. 2 squared plus 1, so that's 2/5, right? 2 over 5. So that's the value of the function f at the endpoints. Now, what's the value of the function f at the critical points inside the interval? So here, guys, be careful. So I got 2 critical points, right? +1, -1. However, the -1 is not inside my interval, right? So my my -1 is not, this is not inside my interval, right? The interval 0, 2. So here, and this is step number 2, I have to evaluate f only at +1, not at -1. Okay, so just be careful here. So we don't evaluate. Is there a question? Oh yeah, okay. So don't evaluate at -1 because it's not in the interval 0, 2, right? Because it's not in the interval 0, 2. All right, so f +1, that will be 1 over 1 squared plus 1, and that will be 1 over 2. Okay. Now I got f of 0, f of 2, f +1. I don't evaluate f at -1 because it's not inside my interval. So I don't really care about it because it's not in the, it doesn't belong to my interval. So now I'm gonna move to the step 3 and check which value is the largest one and which one is the smallest one. Well, obviously the largest one, so we have 0, right? We have 2 over 5 and we have 1 over 2, right? So 2 over 5, this is like, you know, this is like 0.4. And half, of course, is 0.5, right? So what will be the largest value? Of course, that will be the half, right? So f of 1 equal to half, right, is the largest value. So f of x has a global maximum, all right, at x equal to 1, all right, in the interval 0, 2, of course. And so this is at x equal to 1. And what will be the smallest value? Well, that will be 0. So f of 0 which is 0, is the smallest value. So f of x has a global minimum at x equal to 0. All right. Any question, guys? I see there's a question. Let's see, Austin. Yes, so it cannot be used because it's not in the interval 0, 2. Yes, absolutely, Austin. Yes, yes, absolutely, yes. Yeah, that's so you have to be careful about it. Yes, yes, absolutely. So it's because it's not in my interval, so we don't really care about it. Okay, yeah, absolutely. Otherwise, if let's say -1 was in my interval, then you're gonna have negative half, and negative half would be the smallest. So then, yeah, then the negative one would be like the global minimum, but it's not in my interval, absolutely. So that's why you have to check. You have to check that if your critical point is in your interval. Yes, yes, very good. Nice. Yeah, that's a good point. Any other question, guys? Okay, that's good. So then, actually, we are done. Yes. Anyone? Nope. Okay. So yeah, so we are done with this section 3.1. So I can move to the section 3.2. Section 3.2 is also kind of a short section, and then I'm gonna cover section 3.3, which is the most important section in chapter 3. In section 3.3, we're gonna use the derivative to sketch the graph of functions, right? So now let me move to the section 3.2. So section 3.2 is about the mean value theorem, which is, I would say, one of the most interesting theorem in Calc 1, okay? So this mean value theorem. Well, before the mean value theorem, we have another theorem, which is kind of like a particular case of a mean value theorem. So first, I'm going to start with the Rolle's theorem. Okay, so Rolle's theorem. All right. So what does it say, this Rolle's theorem? Well, it says the following. So suppose that I have a continuous function, f of x is continuous on the interval AB. So this is actually kind of consequence of our previous theorem. The theorem we used to find the global maximum and global minimum. So we said if you have a function which is continuous on a closed interval, then you know that f has an absolute maximum and absolute minimum. And so if f has an absolute maximum or absolute minimum, then you know that the derivative is going to be 0, right, at the absolute minimum or the absolute maximum. So the Rolle's theorem says almost the same thing. So it says if you have continuous function on closed interval, and also suppose that f of x is continuous and differentiable. And differentiable, it means that derivative exists. Anyway, we are interested in the derivative, right? So we want the derivative to exist and differentiable on the open interval. Okay. And you need f of a to be equal to f of b. Okay. Then you know that then there exists c in the interval AB, such that f prime of c is 0. All right. So the idea of this theorem, the idea is the following. So again, as I said, you have, you have a continuous function, differentiable on this interval AB, right? So we said in the previous section, we said that f would have an absolute maximum and an absolute minimum, right? Because it's a continuous on a closed interval, right? But the thing is, here, your global maximum or your global minimum could be the endpoints of the interval, okay? So if you want to remove this, the hypothesis that your global maximum or global minimum occur on at the end points, then you have to add this assumption, this one here, f of a, that f of a is equal to f of b. Okay, so then we are saying that there exists a c. You know that your function is going to have a global maximum or a global minimum, right? So then you have the existence of a number c such that the derivative of f at c is 0. So anyway, so what we are saying is that because, so you have you have your a, so this is your a, this is your b, and so let's say f of a is equal to f of b, right? So so let's say this is my f of a, and f of a is supposed to be f of b, right? So they are equal. So then so f of a is equal to f of b. Okay, so then when you connect the points, these 2 points, at somewhere you're gonna have an absolute minimum or an absolute maximum, right? So then this point here, right, would be an absolute maximum, right? So here, let's say this is your C. So then f prime of C, would be 0. Okay, because that's an absolute maximum. Right? This is an absolute maximum. So if it's a maximum or minimum, remember guys, we said if your function has an absolute maximum or a minimum, then the derivative would vanish at C, right? So that's an absolute maximum. So that's why f prime of C is 0. Okay. So the only difference with the previous theorem we had, so remember we had the theorem which says that if you have a function f continuous on a closed interval, right, then f has a global maximum and a global minimum. The thing is, the global maximum or global minimum for your function f, they could be your endpoints. Okay, so here what we are saying is that your global maximum or global minimum, it's not at the endpoints, right? So your C here is in the open interval AB, right? So it's your C is not A, and your C is different from A and different from B. Okay, so this C here is not, it's different from A and different from B. Okay. So to exclude A and B, so that's why we are adding this hypothesis that this f of A is equal to f of B. So then your absolute maximum or your absolute minimum would be somewhere inside the interval AB, but not at the endpoints, right? Not at A or at B. Okay. Anyway, so so let me just say something here, guys. When you say the derivative f prime of C is 0, remember the derivative, the geometric interpretation of the derivative is supposed to be, the slope of your tangent line. So if f prime of C is 0, so it means that the slope of the tangent line is 0. Okay, so now which kind of line has a slope 0? So that's when you have a horizontal line. So when you have a horizontal line, then the slope is 0. So this is your tangent line here. You see this line? This is your tangent line, right? And it's a horizontal line, right? So when you have a horizontal line, the slope is 0. Okay, so that's why this f prime of C is 0. You see, when you have an absolute minimum or absolute maximum. So because the tangent line would be a horizontal line, right? So horizontal lines or the slope of horizontal lines is 0, right? So the slope of horizontal lines is 0, okay? So that's why your f prime of c here again is 0, because the slope of your tangent line is just a horizontal line, right? So the tangent line here, its slope is actually 0, which is f prime of c, right? It's equal to 0, right? Anyway, so now, so you may ask why this theorem is useful, right? So let me show you an example. So why this theorem could be useful, okay? So example. For example, let's say you want to prove or show that the equation f of 2x, let's say 2x minus 1 minus sine of x equal to 0, okay, has at most one solution. Okay, so we have this equation 2x minus 1 minus the sine of x equal to 0, and we want to show that this equation has at most one solution. Okay, so so when I say at most one solution, it means that it cannot have more than one solution, right? So it cannot have like 2 solutions or 3 solutions, etc. Right? So it cannot have. So in other words, it cannot have more than one solution. One solution. Okay. So again, when I say at most one solution, it means either no solution or one solution. So at most one solution. It cannot be more than one. All right. Okay, so you may ask, what's the relation with the Rolle's theorem? Well, so let me explain now how we use it, how we use the theorem, the Rolle's theorem, to prove that actually this equation has no more than one solution, right? So to prove that this equation has no more than one solution, guys, so we're gonna use so we're gonna try to prove it using a contradiction. Okay, so what I'm gonna do, I'm gonna suppose that I have, let's say, 2 different solutions. Okay, and then I'm gonna suppose I have 2 different solutions, and then I'm gonna end up with some contradiction. Okay, and so if I get a contradiction, it means that I have then it means that my hypothesis is wrong. All right. So so what I'm saying is first, so I'm gonna suppose we have two different solutions. All right. So I suppose I have two different solutions, and then I'm gonna try to use the theorem. I will show you how to use the theorem, and then I'm gonna get something which is sort of contradiction. All right. And so if I have a contradiction, then it means that my hypothesis. So this is my hypothesis. So my hypothesis is that we have two different solutions of this equation, right? That's my hypothesis. This is my hypothesis. Okay? So that's what I suppose. Okay, now I'm gonna use the theorem and I'm gonna get some, contradiction, right? Then it means that my hypothesis is wrong. I cannot have two different solutions, right? So what I'm saying is, so the idea now is, to have a contradiction. And so my hypothesis is wrong. So when I say my hypothesis is wrong, it means that I cannot have two different solutions. And what does it mean you cannot have two different solutions? Well, it means that you can have no more than one solution, right? That's like the opposite of having two different solutions. If you cannot have two different solutions, it means that at most you can have only one solution, right? All right, so now I'm gonna suppose we have two different solutions, and let's see how we get the contradiction, right? So let's suppose this is so I have my f of x. I wanna solve, so my f of x is, this 2x minus 1 minus sine of x, right? That's my f of x. Okay. So I'm gonna suppose I have two solutions. So I'm gonna suppose we have two solutions. So what does it mean having two solutions? It means that we have two solutions. F of A equal to 0 and f of B equal to 0. Okay, so that's what I mean by having two solutions. So two solutions of f of x equal to 0, right? I want to solve f of x equal to 0. So when I suppose I have two solutions, I mean I have two different numbers, a and b, such that f of a is 0 and f of b is 0. All right, so I suppose I have two solutions, f of a equal to 0 and f of b equal to 0. So here you see, guys, f of a is the same as f of b. So this is like in my Rolle's theorem, right? You see, in Rolle's theorem, we need f of a, we need f of a, oops. So we need f of a to be equal in Rolle's theorem. Let me zoom out. Okay, so in Rolle's theorem, we need f of a to be equal to f of b, right? So here, f of a is 0 because a is a solution of f of x equal to 0. F of b is also a solution, so f of b is 0. So then my f of a is equal to f of b, right? This is here. F of a is equal to f of b is equal to 0. right? And that's exactly my the hypothesis in my Rolle's theorem. So then by Rolle's theorem, so I have this function f, which is continuous, let's say on this interval AB. Then, so what does it imply, the Rolle's theorem? So the Rolle's theorem says that then you know then there exists a number c in the interval AB, so that the derivative of f at c is 0, right? So by Rolle's theorem, I know there's a number c in the interval such that the derivative is 0, right? So I know there's, so by Rolle's theorem, so by Rolle's theorem, there exists a number c in the interval AB, there exists a c in AB, the interval AB, such that f prime of c is 0. Okay, so that's my Rolle's theorem, right? You have f of a is equal to f of b. Your function is continuous, so then you know that there's a number c in the interval, such that in the interval AB, such that f prime of c is equal to 0. So your c could be your global maximum or global minimum. All right. Anyway, but you know there exists at least a number c says that the f prime of c is 0. Okay, now, so now you may ask, what is the contradiction, right? Because we don't see any contradiction here. But the thing is, if you compute f prime of x, so on the other side, on the other hand, what's f prime of x? Well, f prime of x is equal to the derivative of 2x, that's 2 times 1, minus derivative of 1, constant by itself is 0, minus derivative of sine of x is cosine of x. All right, so my f prime of x is equal to 2 minus cosine of x. Okay, that's my f prime of x, that's my derivative. Right? Now the question is, again, where's the contradiction? Well, here's the contradiction. So the contradiction is the following. So the Rolle's theorem says that there's a number c such that f prime of c is 0. Now, if you try to solve f prime of x equal to 0, so if you try to solve f prime of x equal to 0, well, let's see. So let's solve f prime of x equal to 0. So then that's 2 minus cosine of x equal to 0. So that's 2 equal to cosine of x. Okay, but that's impossible, right? Because cosine of any angle x is always between -1 and +1, right? So because cosine of x is always between cosine of any angle is always between -1 and +1. So this is impossible. Okay, so which means that there is no solution of f prime of x equal to 0. So it's impossible to have f prime of x equal to 0. There is no such value of x, right, for which the derivative is 0. That's impossible, because when you solve the derivative is equal to 0, you get cosine of x equal to 2. That's impossible. So the derivative cannot be 0. So what I'm saying here is that the derivative, so the derivative f prime of x, it cannot be 0. It cannot be 0, right? But on the other hand, Rolle's theorem, we said, Rolle's theorem says that there exists a number c in your interval so that f prime of c is 0. But that's not possible. I just concluded that it's impossible for a derivative to be 0, right? So that's my contradiction. So the contradiction is on one side, Rolle's theorem says that there is a number for which the derivative is 0. And on the other side, when I try to solve the f prime of x equal to 0, there is no solution. That's impossible to have a derivative is equal to 0. So that's the contradiction, right? So now I have a contradiction, right? So that's my contradiction. So sorry. So we have a contradiction. Okay. Again, why we have do we have a contradiction? Because Rolle's theorem says there is a C. There is a C such that you know, f prime of C is 0. Okay, but then when I solve f prime of x equal to 0, there's no solution, right, to f prime of x equal to 0. That's impossible, right? So, but on the other hand, on the other side, my f prime of x cannot be 0. Okay, there is no solution to f prime of x equal to 0. Okay, so that's why we do have a contradiction here, right? Because Rolle's theorem says that there's a C for which the derivative is 0, but when I try to solve the derivative is equal to 0, that's impossible because cosine of x cannot be equal to 2. Cosine of x is always between -1 and +1. So if we have a contradiction, then that means that the hypothesis, our hypothesis is wrong, right? The hypothesis that we have two different solutions is wrong, okay? So then the hypothesis is wrong. So then the hypothesis is wrong. And my hypothesis was that I have two different solutions. So we cannot have two different solutions. We cannot have two different solutions. And so two different solutions. All right, and so then I can, and that will be the proof. So then, the equation has at most one solution. So the equation, you know, 2x minus 1 minus sine of x equal to 0 has no more than one solution. One, just no more than one. Okay. So see, guys, this is kind of, so we are trying to use like kind of, you know, this is like a kind of logical thinking. You have to use a contradiction to prove your, you know, to prove that your equation has no more than one solution, all right? And of course, we're using the Rolle's theorem. Any question, guys? Okay, so here's an exercise. Show that the equation x fourth plus 4x plus, let's say, 199 equal to 0, okay, has at most two solutions. Two solutions. Two real solutions, of course. Two real solutions. Okay. All right, guys. I mean, you have to apply. It's the same idea, right? You have to apply. So here, you have to prove that this equation has at most two real solutions, right? And again, so what we're gonna do, we're gonna try to apply to find the sort of contradiction, right? So you want to prove that it has at most two real solutions. So you can suppose that your equation has, let's say, three different solutions, all right? Three different solutions, and then you're gonna apply your Rolle's theorem, and then you're gonna end up with a sort of a contradiction, and so then your hypothesis would be wrong, okay? And so then you can conclude that the equation has at most two real solutions. Okay, so I'm gonna give you a couple of minutes, guys, to think about this exercise, all right? So it's the same steps. I mean, the idea is the same. You have to suppose first that here, so in the example, in my example, I had to prove that the equation has at most one solution, right? It's at most one solution in my example, one solution. Here in this exercise, it's at most two solutions, right? Is at most, where is it? At most two real solutions, right? But the idea is the same. I want to prove that here in the example, I want to prove that the equation has at most no more than one solution. So I suppose that the equation has two different solutions, right? So, okay, that's one more than in the problem. Okay, so in the exercise here, we have to prove that the equation has at most two real solutions. So in your hypothesis, you're going to suppose that your equation has three solutions, right? One more. So it's you have to suppose that it has three solutions, right? And then try to use the Rolle's theorems, and then see if you get you can get some contradiction. All right. So I'm going to give you a couple of minutes to think about this exercise. All right, guys. We have like 7 minutes. So I'm gonna try to go over this exercise in the last 7 minutes. So as I said, the idea is to use a proof by contradiction, right? So we're gonna suppose, so we want to prove that the equation has at most two different real solutions, right? No more than two solutions. Okay, so I'm gonna do, I'm gonna use a proof by contradiction. So I'm gonna suppose that I have three different solutions. Okay, and then I'm gonna use my Rolle's theorem, and then I'm gonna end up with a contradiction. Okay, so the contradiction of course means that my hypothesis is wrong. Okay, and if my hypothesis is wrong, then it means that the converse would be true. So if my I suppose that I have three different solutions, and so that if that's wrong, then it means that I have no more than two solutions, right? So yeah, so we're gonna use a proof by contradiction, proof by contradiction. Okay, so I'm gonna suppose, so here's my hypothesis. I'm gonna suppose we have three different solutions. Okay, let's say A, B, and D of my equation. So of let's say f of x equal to x fourth plus 4x plus 199 equal to 0. Okay, so I'm gonna suppose I have three different solutions. Let's call these solutions A, B, and D. So of my equation, right? So I know that my f of A, so it means that my f of A is 0, is equal to 0, because f of A is supposed to be a solution, right? So it means if I plug A in the function f, I get 0 because it's a solution, right? So it's f of A is supposed to be 0, f of B is also 0, and also f of D is 0. Okay, I have three different solutions of this equation. Now, I'm gonna use Rolle's theorem, right? So a Rolle's theorem, I need an interval AB. So here, let's say I have, without loss of generality. So let's say you have first, I'm gonna take the interval. So let's say A is less than B is less than D, okay? Without loss of generality, right? So, so let's take, if you take the interval AB and apply, so I'm gonna apply Rolle's theorem in the interval AB. Right, in the interval AB. So what does it say, the Rolle's theorem? So, well, f of A is equal to f of B is equal to 0. Okay, so then there exists a C. So then there exists let's say C1 in the interval AB says that f prime of C1 is 0. So I have a solution of the derivative equal to 0, right? Now, if I take the, let's say if I apply the Rolle's theorem in the interval BD, okay, I'm gonna get a different solution, right? Apply Rolle's theorem in the interval, let's say BD. So, you know, f of B is supposed to be equal to f of D, supposed to be equal, then equal to 0. So by Rolle's theorem, then there exists C2 in the interval, you know, BD, right? We're talking about this interval BD, says that f prime of C2 is 0. Okay, so if you want to visualize this, guys, so what I'm saying is the following. I mean, what I'm saying is, you know, I have A, I have B, and I have D, right? And all I'm saying is that f of A is 0, f of B is 0, and f of D is 0. So then let's say I have something like this here. F of A is 0, right? F of B is 0, and then f of D is 0. And all I'm saying is that there's, you know, there's a C1 here, there's a C1 here, says that because this is, you see, this is a global maximum, so then f prime of C1 is 0. All right. And then also between B and D, there is a C2, a number C2, you know, it's actually a global minimum, says that f prime of C2 is 0. Okay. So that's all I'm saying using this Rolle's theorem. But the thing is, so Rolle's theorem, so it means that I have two solutions of my derivative equal to 0. So then C1 and C2 are solutions. So then C1 and C2 are solutions of f prime of x equal to 0, right? They are, I mean, C1 is a global maximum. Global maximum, C2 is a global minimum. So both are solutions of f prime of x equal to 0. Now, let's see if we can have two solutions of f prime of x equal to 0. So what's f prime of x? F prime of x, you know, f of x was x fourth. So that's 4x cubed. 4x cubed plus, then we have 4x, derivative of 4x, they're going to be 4 plus 4. And then the derivative of 199, that's 0. So if you try to solve f prime of x equal to 0, that's 4x cubed plus 4 equal to 0. So then 4x cubed would be negative 4. You divide by 4, so that's x cubed equal to negative 1, right? I divide by 4 here. By 4 here and by 4. So x cubed is negative 1. And then we apply the third root. So this is my third root. Third root. There's no plus or minus because it's a cube, so it's an odd power. And so x, there's only one solution. So third root of negative 1, it's negative 1. So x is negative 1. All right. So what I'm saying here, guys, is there's only one solution. There is only one solution of f prime of x equal to 0. There's only one solution, exactly one solution of f prime of x equal to 0, right? Only one solution. But Rolle's theorem said that I have actually C1 and C2 are solutions of f prime of x equal to 0. So Rolle's theorem says that I have two different solutions of f prime of x equal to 0. But when I solve f prime of x equal to 0, I get exactly only one solution, right? So that's a contradiction. That's impossible. Okay, so the two events, they cannot happen at the same time. So I cannot have, like, one hand, two different solutions of f prime of x equal to 0, and then on the other hand, I actually have only one solution, right? So that's contradiction, right? So that's a contradiction. So then contradiction. And so my hypothesis is wrong. Hypothesis is wrong. So I cannot have more than two solutions. So hypothesis is wrong. My hypothesis was I had 3 different solutions. All right, 3 different solutions. So that's wrong. That's impossible. So the conclusion is that we can only have no more. We can only have no more than 2 solutions. No more than 2 solutions. We cannot have more than 2 solutions, right? Okay, guys, I'm sorry. It's 49. I'm sorry, I went over time. So I'm gonna stop here, all right? I guess I will see you next Monday, and I will continue with this section 3.2. All right. So thank you, everyone, and good night. I will see you next Monday. Thank you, guys.
Thank you, Professor.
Thank you. We'll see you next time. Take care.